Dear colleagues, please let me introduce you the paper dedicated to comparative analysis of face ROI outline algorithms for contactless heart rate measurement under different registration conditions. During the presentation, we are going to discuss basics of video plethysmography technique, describe the problem and solutions we propose, describe experiment issues, and discuss results. Video plethysmography (VPG) is a contactless pulse curve recording technology based on processing the video stream of a face image followed by time-frequency analysis of the signal in order to calculate physiological parameters. Various modifications of methods for video images processing and VPG signals are presented in literature aimed at increasing heart rate HR measurement stability while reducing the influence of image registration parameters and taking into account the physiological features of facial blood flow. A VPG signal acquisition model can be described using the given equation. This expression allows to select several research areas at once. Evaluating the effectiveness of different approaches to processing facial images under different registration conditions, and splitting the integration area into smaller areas with independent analysis of the received signals, which allows to ignore areas of the image with a low signal-to-noise ratio, SNR. The purpose of this work is a comparative analysis of various algorithms for ROI outlined in a face image under different signal registration conditions. The area of color space which contains the distribution of human skin colors is quite limited. Thus, segmentation of the required face area can be reduced to 16 pixels belonging to a cluster defined by a parallelepiped which borders are known and defined in literature. The value of the VPG amplitude corresponding to the ith frame of the video image of the face is calculated using the given formula, where I is the frame number of the video image, j, k are the coordinates of the pixels belonging to the selected area, RGB are the color coordinates of the corresponding pixels. An example of the result of an algorithm based on the color segmentation method is shown on the slide. Since the selected area in the image has a characteristic geometry, it makes sense to rely not only on its shape in the color space, but also on the standard metric representation. The dlib Open Library provides methods for segmenting 68 points of face contours using a histogram of oriented gradients. By cropping the image along the contours, one can get an image with pixels containing information only about the human skin. The contour that bounded the desired area was based on landmarks that described the eyebrows and the lower part of the face. The eyes and lips that fall inside this contour were blackened before calculating the VPG signal. Image on the slide shows an example of how this algorithm performs. Combining operations in both metric and color spaces allows to use areas of skin that do not fall inside the contour drawn with facial landmarks and at the same time has the property of adaptability to the lighting parameters of the biological object. Segmentation of the forehead and exclusion of hair are possible if the distribution of pixels shifted in the color space is correctly analyzed during the operation of the algorithm based on facial landmarks detection. Calculations have shown that the RGB coordinates of points belonging to the areas selected by this method are approximated by a linear function. Thus, the combined algorithm consists of the following steps. First, facial landmarks detection. Second, selecting a contour based on detected points. Third, calculation of coefficients of a linear function f that approximates a point cloud in RGB space based on pixels inside the selected area. Fourth, search for pixels outside the selected contour where the following expression is valid, where I is the Euclidean distance from point P to the approximating function f and nu is the average distance between the color coordinates of pixels belonging to the selected contour and the approximating function. An example of the algorithm result is shown on the slide. In previously described algorithms, frame of the video corresponds to a single count of the VPG signal, which takes into account all pixels belonging to the selected area. It can potentially worsen the signal-to-noise ratio if there are any uninformative areas in the selected area of the image. Building the grid with the nodes at facial landmarks allows to calculate VPG for each sector of the grid independently. This permits to exclude noisy skin regions and take into account phase distribution of the pulse wave along face surface. In this work, 68 facial landmarks were detected and 56 points were used for creating the grid. The grid was made up of rows and columns with lines parallel to image borders. An example of an image divided into sectors is shown in the figure. According to the purpose of the technology under study, it is obvious that the main metric of the effectiveness of the image processing algorithms should be based on the error of heart rate measurement using the contactless method. Let's consider video plethysmography signal being good if the heart rate measurement error is equal or less than 1 bpm. Acceptable error rate, 1 bit per minute, is chosen according to the pulse oximeter test recommendations if the signals have a sufficiently long duration endpoints. It is advisable to divide them into smaller sections with the size of k points. The final metric for the quality of a contactless photoplethysmogram signal is the share of signal pieces where heart rate error is less or equal to 1. The heart rate calculation is based on the localization of systolic peaks in the signal with a peak detector using wavelet transform, followed by the calculation of the average time interval between peaks. The illumination of a biological object and the distance between the registration tool and the biological object were used as parameters that simulate video recording conditions. The illumination was changed by means of dimmed lamps and controlled by a luxmeter. The distance between the camera and the face of the subject was measured using a laser rangefinder. Two series of measurements were performed. In each, one of the parameters was changed and the second was maintained at a constant value. Thus, when changing the distance between the camera and the subject's face, illumination was maintained at the level of 1000 lux. When the light intensity was changed, the distance between the bio-object and the registration tool was equal to 60 centimeters. The measurements involved 4 subjects, each of whom underwent parallel registration of the video of the face, and contact PPG 3 times at a given value of the controlled environmental parameter. The duration of each measurement was 30 seconds. Thus, for each value of the controlled parameter, the signals were registered 12 times. For each of the VPG signal, the value of the signal quality metric was calculated using the given formulas. To check whether Q vectors are well modeled by normal distribution, Shapiro-Wilk test was performed. Checking the statistical significance of the difference between Q vectors from different algorithms with the same parameter values was performed using the student's t-test. Figures on the slide show the dependence of the average value of the metric on the illumination of the subject's face and the distance between the face and the registration tool respectively. Analysis of the measurement results allows us to conclude that the algorithm based on an independent analysis of individual sections of the face image showed the best result in terms of the value of the efficiency metric. there was no statistically significant difference between the values of the performance metric for the other three algorithms. The paper is devoted to the comparative analysis of algorithms for ROI outline on face images in the task of contactless heart rate measurement. The operation of 4 algorithms based on color segmentation and the use of facial landmarks was studied under different illumination conditions of the subject's face and also at different distances between the camera and the subject's face. The results suggest that the algorithm based on the grid with the nodes at facial landmarks with independent video plethysmogram calculation for each sector shows best measurement accuracy and stability.